Greetings, finance aficionados. In this video, we're going to work through several different time value of money problems, and we're going to see what happens when our compounding periods are something other than 1 year. For example, what if our money is compounding twice a year or 4 times a year? And then observe the effects of that compounding. So before we begin, we want to make sure that we remember that in finance, interest rates are typically stated in annual terms. So in this problem, it says if we have $1,000 today and it compounds once per year for 10 years at 6% annually, how much will we have at the end of 10 years? Okay. Now, even if this didn't say 6% annually and it only said our money is compounding at 6%, we would understand that that means annually, because in finance, interest rates are typically quoted in annual terms unless otherwise indicated. So if our compounding periods are not annual periods, then we have to make some adjustments, and that's what we're going to do in this video. But first, let's do a basic one where the compounding periods are annually. So in this one, we have $1,000 today. So present value, PV, is the beginning value. So we know that it says $1,000 today. And it compounds once per year for 10 years at 6% annually. So once per year for 10 years, okay, that's 10 compounding periods and 6% annually. Now, N, we want to remember, is the number of compounding periods over the entire length of the period or the timeline covered by the problem. And the I is the compounding rate per period. And since our periods are annually, we'll use the 6. So we need to find the future value, because how much will we have at the end of 10 years, which is in the future. So we'll go over to the BA2 Plus, clear out any previous time value memories. So these are the buttons we're going to be using. N for number of periods, I for compounding rate per period, present value, we're not going to be using the payment in this illustration, and future value. So to access these uppercase functions, here are what I call the uppercase functions, these functions above the buttons, we first hit the second button. So we hit second, and we clear out time value memories, see CLR-TVM. That's real important to do in every problem before you start every problem, because the numbers that we're going to be putting under these buttons stay there until we erase them. So if we have numbers lingering under some of these buttons from previous problems, it could throw our results for this problem way off. So we always do second, clear time value memories before we begin. And that second, again, accesses these functions that lie above the buttons, kind of like a shift key on a keyboard. All right, so let's go ahead and punch in our numbers. Present value is 1,000. I'm going to put this, change the sign to make it a negative, signifying an outflow. Remember, when we're using these buttons here, and the same works the same way in Excel and other calculators, and is that it assumes the money is being invested, going out, and then we have money coming back, coming in, and so it distinguishes that outflow and inflow of cash by using a negative to indicate an outflow and a positive number to indicate an inflow. Doesn't mean less than 0 necessarily when we're using these buttons. Okay, so $1,000, hit PV. PV equals $1,000. N is 10. So 10, we go up to N, click N. So N equals 10. I is 6, so we first click on 6, and then I. Now all that's left is to solve for the future value. So we compute for the future value, and we get roughly 1791 if we round up a little bit. Okay, so I'm going to type it 1791. So that's how much we would have at the end of 10 years if our money was growing at 6% a year and compounded only once per year. So let's go down to the next version of this problem. Okay. Now this one, kind of the same thing, only our money is compounding twice per year for 10 years at 6% annually. How much will we have at the end of 10 years? So that requires us to make some adjustments. So I'm going to clear this display so we don't get confused here. All right, present value. How much if we have $1,000 today? $1,000 present value. Compounds twice per year for 10 years. Now remember, N is the number of compounding periods over the entire length of time covered by the problem. So if we're compounding twice per year for 10 years, then we have 20 compounding periods. In other words, 2 times 10, twice per year for 10 years. Okay, 20 periods. Now, if the annual rate is 6%, if the annual rate is 6%, but the length of our compounding periods is half a year, so what we have to do is take that 6 and divide it by 2, and then we end up with 3. So I is 3 in this case, because our compounding period is a half a year, so we take half the annual rate. So now we can punch the numbers in. Again, always clear things out. Second, clear time value memories. $1,000 goes under present value. 20 goes under N. And 3 goes under I. And now we compute for the future value. 1806. Now that's a little bit more than what we had previously. And that's one of the things we want to observe. So it was 1806 here, but when we were only compounding once per year, it was 1791. So let's do another one. If we have $1,000 today and it compounds 4 times per year for 10 years, so now we're compounding quarterly. All right, so I'm going to clear out this old problem here and punch in the numbers here. Again, the present value is 1,000. N, remember, is the number of periods covered by the problem. So we have 4 times per year for 10 years. So 4 times a year for 10 years is 40 compounding periods. It's 6% annually. Well, if 6% is annual and we're compounding 4 times per year, then we have to take that annual rate and chop it into fourths, and we end up with 1.5. Okay, and we'll compute for this. Now I'll show you when you're doing this on the calculator, you can actually do this calculation over there, and it makes it a little bit easier. You don't have to do it twice. So let me demonstrate. Second, clear time value memories. 1,000 goes under present value. 40 goes under N. And I, we know it's 6 divided by 4. So we'll just do the calculation here and get our 1.5. Now we'll put that under I. and then compute for future value. 1814, which is a little bit more than we had even before when we were compounding 2 times per year. So let's do one more. What if our money is compounding monthly? Okay, the present value is $1,000, and it's compounding monthly for 10 years. Well, monthly for 10 years is 10 times 12, right? Because there are 12 months in a year. So we have 120 ends. Again, we could do this calculation over here that way as well as we're punching it in. And here, 6 divided by 12 this time, because our annual rate's being chopped up into 12 pieces, 12 periods per year, and that, of course, ends up being 0.5. So let's plug in the numbers. Second, clear time value memories. 1,000 goes under present value. Let's just do this calculation over here. Monthly for 10 years. So 10 times 12 months per year is 120, and that will go under N. I is the annual rate of 6 divided into 12 pieces, or 0.5 per period. That goes under I. And we'll compute for future value. 1819, if we round. Which is the largest amount so far. So let's take a look and compare the results here of these things. Remember, each one of these was for 10 years at an annual rate of 6%. Okay. And with annual compounding, we ended up with 1,791. With semi-annual, or every 6 months compounding, we got 1,806. Okay. If we compounded 4 times per year, we ended up with 1,814. And with monthly compounding, we ended up with 1,819. So the number of compounding periods per year matters. The more times something compounds per year, the faster it grows. So that's something to keep in mind when we're looking at different types of savings programs or whatever. The more frequent the compounding, the faster the money grows. And that's all for this one.